headquarters. And I used to do my PhD with Laurent Bopp and Lester Kwiatkowski at IPSN in Paris. And I'm gonna talk essentially about one work we led with Lester and Laurent at that time, related to the coral calcification decline and the impact on the ocean carbon sink. And I wanted to start with a perspective. I mean, it's kind of a perception I have, and which is key in my way to get inspired also in terms of climate change communication. I have the feeling that we have two climate sentinels, two types of ecosystems or landscape, seascape, which are climate sentinels. We have glaciers on land, and we have coral reefs, or we could even extend it to benthic calcifiers for the ocean. And they used to be impacted by human activities in the past, but really now they testify climate change. And we can see with our eyes, basically, that glaciers are melting. We can see with our eyes that coral reefs are bleaching and even degraded and could die even at some point. So, and talking about glaciers and coral reefs, for me, when we talk about climate change, we can cover all the topics around climate change, radiative forcing, carbon cycle, biodiversity as well. And that's what we're gonna talk with coral reefs here. And please take some notes, because if you look at what is written in the IPCC, in the latest IPCC report, you will read some stuff like this. Due to the impacts of warming and to a lesser extent ocean acidification, global reef carbonate production is estimated to decline 71% by 2050 in SSP 1 to 6. SSP 1 to 6. So it's almost sure that this will happen. And you can also read, for instance, coral reefs are under threat of transitioning to net erosion with a global warming above 1.5 degrees Celsius. So it all depends on how hungry we are related to the carbon pie. And I mean, when we talk about this carbon pie for the 1.5 degree target, we are so close to it. It's like, I'm French, so it's like if we talk about a camembert, you talk about this cheese, and this is the piece left, and we are all like this. So it doesn't smell good for coral reefs. Let's say that this cheese doesn't smell good, and it doesn't really smell good for coral reefs. And coral reefs are pointed in the literature as a tipping element in the Earth system. At least if you look at literature regarding tipping elements, you will find coral reefs, but mostly for the ecosystem tipping elements. And for instance, in this study by Wunderling and co-authors in 2024, you can see that coral reefs are not considered as having a potential global feedback on global mean temperature. If you look at Lenton and co-authors 2023, a huge report on tipping elements in Earth system model, in the system, you can read that coral reef decline does not substantially feed back to the climate system on policy-relevant timescales. And this is a bit of a surprise to read this in the literature. I mean, I feel like the literature around coral reefs is so abundant and it covers so many topics, and that's also very difficult to find global analysis. It kind of muddy the waters. I have the feeling this huge literature around coral reefs. In France, at least in French, what we say is that it's to drown the fish in the water. So you can try like this if you want. You can try to be a bit more harmful and violent, and this is kind of what we are doing with coral reefs. And if we come back to our coral reef, basically, in the 80s and 90s, the coral reef feedback on climate was extensively discussed. There was this coral reef hypothesis led by Berger in 1982, for instance. There was then this coral reef CO2 sourcing debate, and you see that the authors of these studies are really famous. I mean, we're talking about really extremely good scientists and extremely well-known scientists. And in some papers, you can find that basically, coral reef, when they calcify, they are a CO2 source, but it's It's relatively negligible compared to at that time the CO2 related to fossil fuel combustion, about 1% of this amount. So it's small, but it's small. But well, if you look at what's happening today in our community, so many people working on CDR, and if you look at even CDR taken into account in carbon budgets now, it seems crazy. If you look at, for instance, the actual amount of CDR, most of it is conventional CDR at the moment. It's not most of it, it's almost all of it is conventional CDR related to forest land use. And when we talk about other CDR, marine CDR, whatever, it's so tiny. And why not then focusing a bit more on coral reefs and the feedback on the carbon cycle? What is also surprising is that if you look at the latest IPCC reports, you will find a table related to unresolved feedbacks in the Earth system models. And we find stuff around forest, around permafrost, but nothing about coral reefs. So that's our question here. What about coral reefs? What is the feedback of coral reefs? So it will impact the tropical restoration. We have, this will happen with a high or very high probability, and to what extent this will affect the carbon cycle and on what time scales. That's our question, basically. And I will essentially present what we published with Lester and co-authors this year, very recently in PNAS. And so just coming back on the two major threats for coral reefs at the moment, the first one is related to excess heat with increasing ocean temperature, increasing also intensity and frequency of marine heat waves. And on the other hand, you have this increase in the CO2 content in the atmosphere leading to ocean acidification. So we based our work with Lester and co-authors on this study by Cornwall and co-authors in 2021, which is a meta-analysis of experimental methodosm and in situ estimates of coral reef net calcification under each RCP. And they look at basically all the different calcifiers, they look at all the different dissolution processes, and they try to sum it up like this, producing a value for the net carbonate production at present day in coral reefs, so it's positive, there is net accretion. And then if you look at what happens in the future, you see there is in 2050 a shift towards net dissolution or medium to high emission scenarios. And this is not driven by warming, not driven by acidification, not by the combination of the two, but essentially by bleaching. And if you look at what happens in 2100, it's basically the same value as in 2050 with these negative values for the medium to high emission scenarios. So we have information from this study regarding the relative change in the net carbonate production for coral reefs. And then what we did is kind of a global value of what is buried in coral reef ecosystems. So we wanted to get orders of magnitude. So what we did is use some inputs from Cartapenis and co-authors 2018, saying that, yeah, in coastal areas, around 150 teragrams of carbon per year are buried as CaCO3. The range is between 30 and 300 teragrams of carbon per year. And let's use it as if it was only coral reefs, linked to coral reefs. So that's what we did. And you see that basically, if you look at the coral reef net carbonate production, the historical production is what drives the magnitude shift in simulated coral reef carbonate production anomalies up to the end of the 23rd century. So that's super important that as a community, we can agree on a specific value for this historical CaCO3 production in coral reef areas. And then what we did is basically we used our model, name of this case, in an offline configuration. We imposed changes in the surface ocean, so changes in terms of alkalinity and the IC, trying to mimic the net, the relative dissolution of coral reefs compared to pre-industrial state. We considered that this dissolution was relative dissolution was homogeneous across grid cells, and we considered that there was kind of an infinite CaCO3 reservoirs in these areas because the stock of CaCO3 was kind of built over millennia, the stock that is currently available. And what we get, if you look at the ocean carbon uptake up to the end of the 23rd century, is that whatever the scenario, there is an increase in the entrepreneurial carbon uptake by the ocean, and it is much more for the medium to high emission scenarios. I'm sorry, but I'm gonna go back to carbonate chemistry again. I think it's super important that we share our ways of talking about the carbonate chemistry in the ocean. We have all different ways to share it, and I think that it's super inspiring to get other ways of communicating about that. So I will do what I think is what I love the most in sharing the carbonate chemistry for a broad audience. What is kind of surprising for someone who is not part of this classifying community is that when coral reefs are dissolving, they increase the ocean carbon content. Okay, but what you would expect if you look at only carbon fluxes, you would expect it to be released to the atmosphere at some point, and this is false. So to understand this, and this was partly introduced by Olivier or Tyler before, you have to come back to this equilibration of CO2, the CO2 reaction in seawater. And basically, you consider two different variables, two different conservative variables, DIC and alkalinity. I do not come back on the definitions of those two. And what is super nice is that when you fix salinity, temperature, pressure, you can work in this alkalinity DIC diagram to plot the pH contours, to plot the PCO2 contours, and basically what it means when you look at RC carbon fluxes, it means that if a water parcel, so the pink point here, is in equilibrium with current atmospheric CO2 concentration, and then the water parcel is on this solid white line. And then from that, you can understand so many processes and how it will impact both the carbon fluxes, the air carbon fluxes, but also the acidity of the ocean. If you move the water mass in that direction, you will acidify and outgas towards the atmosphere. If you move the water mass in that direction, you will basify and ingas. Coming back on organic matter production, you consume CO2, you consume nutrients, so basically you reduce the IC, you deplete your ocean of the IC, and you increase a bit alkalinity. So you will locally basify and push towards an ingassing of CO2. Whereas when you produce CaCO3, you acidify and you tend to outgas CO2 as well, because you decrease 2 times more alkalinity than the IC. So you are on the other side of this solid white line here. So basically, when colors calcify, you deplete your ocean of carbon, and you deplete it 2 times. You are a carbon source for the atmosphere. When you consider dissolution, you increase the ocean carbon content with dissolution of calcium carbonate. But as you modify ocean chemistry, you are also a carbon sink for the atmosphere. So you increase again the ocean carbon content, which can be counterintuitive, really. And it's something we still see in the literature, even in our field. Frédéric Gazot might tell a bit about that, but in aquaculture, it's really a topic. So we'll see what he says in a few days. If we come back to our call with feedback on the carbon cycle, you see that most of the model spread is still determined by emission scenarios, but the impact of coral reefs is not negligible. In fact, so if we look at for each scenario, the ocean carbon uptake enhancements, you see that for RCP 4.5 and RCP 8.5, so the medium to high emission scenarios, the values are quite similar, and it can be up to 0.4 petagrams of carbon per year of increase by the end of the century, or even during the second part of this century. And this is not negligible. When you look at in leading codes and code for 2021, for 76 outputs, if you look at the ocean carbon uptake uncertainty or the model outputs, you see that especially for RCP 4, sorry, 245, you see that 0.4 petagrams of carbon per year is quite of is very close to the model uncertainty range for 76 outputs. So it's not negligible. And what is key with this core wave feedback is that it should go on over the 22nd, 23rd century and even beyond. So it builds up kind of an extra anthropogenic carbon uptake over time. And if you look at cumulative ocean carbon uptake enhancement, okay, in 2100, you might it might be up to 30 petagrams of carbon, but if you look at the end of the 23rd century, it might be up to more than 100 petagrams of carbon not per year. Sorry, I wrote per year, but it's not per year. So it's cumulative. Coming back to this table from the IPCC, you see that the value we get, the maximum value, kind of high-end value for this core with feedback on carbon, 30 petagrams of carbon by the end of the 21st century. It's kind of the same magnitude of boreal forests dieback. It's in the other direction. So it's a sink of carbon in that way. A few more information regarding this core feedback. When you look at the map of the anthropogenic carbon uptake enhancement, you see that this happens beyond core reef regions. Only a fraction of this feedback happens in core reef regions. It's due basically to the residence timescale of seawater in these areas and the timescale for CO2 to equilibrate with the atmosphere. What is also interesting is to look at the alkalinity anomalies in these areas and even for the whole ocean. By the end of the 21st century, you see that alkalinity anomalies are relatively small. It's just a matter of tenths of millimole per cubic meters by the end of the century, which is really small and very difficult to detect when you look at the natural variability at some stations. It's about 100 millimoles of per cubic meter. So it will be difficult to detect it from global measurements like this, looking at alkalinity, at least over the coming years and decades. And regarding acidification, what you would expect is basically if you dissolve calcium carbonate is to increase a bit pH, so to basify slightly your ocean. And this is what happens, but it's really negligible. And this can be understood, I think, pretty easily with this graph again. So you consider this water mass that is currently at equilibrium with current atmospheric CO2, and then you consider the solution. So you will shift this water mass on the graph towards the end of this arrow. And there, as your water mass is no longer in equilibrium with the atmosphere, it will tend to uptake CO2 to reach back equilibrium. And you see that you reach back a bit further this solid white line. And as the solid white line is very similar to the pH contour, the dotted line here, you will have only a very small effect on pH, so a very small effect on acidification mitigation. Regarding this core reef feedback, if we try to sum it up, It will entail a slightly upward revision of the remaining carbon budget if it's taken into account in Earth system models. At the moment, you know this TCRE graph, so you get the temperature increase since pre-industrial era on the y-axis and the cumulative CO2 emissions from today on the x-axis. And you see that we have unrepresented Earth system feedbacks, which shorten the remaining carbon budget. Here, if we take into account the core feedback, it means that we kind of shifted upward and with this remaining regarding this remaining carbon budget. It's also the same regarding the zero emission commitments. Basically, as when if we stop emitting, as coral reefs are really in bad shape, and they're very close to being in a very, very bad shape. So they will tend to keep going on, kind of dissolving over time, or at least relative to the past, they will be not dissolving. So this will reduce the zero emission commitments, and thus increase the remaining allowable warming. I see you already talking about this kind of additional piece of camembert. But if we keep going on as we are, at the moment, this piece of camembert is already roasted, and it's not that much. Let's be true. And I will come back on the biodiversity aspect at the end, but just one more comment on this. So I've been talking about coral degradation and the feedback on the calcium on the carbon cycle, just focusing on net ecosystem calcification, basically, and not production. And that's something we could even do at some point. At least we need a bit more maybe consensus in the literature. But there is an emerging consensus, I would say, saying that there is kind of a shift from coral reef towards macroalgae in the future that is expected due to coral reef degradation. And this shift, if we look at what was done by Davis and co-authors in 2020, means that basically you have and it is a meta-analysis showing that basically in the past, over the past, net calcification, net ecosystem calcification decreased, but net ecosystem production increased. So this would even enhance the coral reef feedback on climate with organic matter production and CO2 uptake then. I have to say that I got kind of trapped in the coral reef research net at some point, but I feel like being a turtle working on this, especially because the literature is so vast and focusing on specific aspects really locally sometimes. So it's very difficult to get a clear idea at global scale. And as a modeler, this is what I really need. So I used to work with Laurent and Lester at IPSL. Now I work with Charlotte. But on this topic regarding coral reefs, we have works ongoing with also Nathalie Boot at IPSL Paris and Adrien Comte on a specific topic regarding the social cost of carbon, because we see that coral reefs might in fact reveal some limitations to the social cost of carbon. I mean, it's not possible to say that it's great to see coral reef degrading. It's a disaster for biodiversity. It might be positive regarding climate, but it's that disaster for many aspects around it. So it's a way to talk about coral reefs. And then, well, this is a dream. This is a work we're currently working on. But it's to implement a coral reef, prognostic coral reef module in Earth system models very soon. And for this, we have I like talking about this four-leaf clover nexus for this modeling aspect. So regarding coral reefs, you need to be good at representing their habitats, their heat wave sensitivity, their calcium carbonate production, and also dissolution, and to try to filter the uncertainties we have for each one of these we've divided our work in specific steps. So first, we're working on habitats and heat wave sensitivity. And basically, the objective at the end is to have kind of a continuity in our work to build a module that is as robust as possible and to be able to use it not only for future projections, but also for paleo aspects. So regarding coral reef habitat, and I will spend a few minutes talking about that because I think it's interesting. It might question a bit the community. So we use topography data. We use also climatologies regarding some environmental parameters, and we question whether we should use seasonal variability also for some of these variables. And just coming back on the fact that I feel like a turtle working on this, I feel very slow working on this. It's because, as I told you, the literature is vast and some information can be confusing. For instance, we are working with two different coral reef data sets at global scale. These are the two data sets we can have. The recent one, the Allen Coral Atlas dataset, and the UNEP WCMC1, which has been built over time. And in fact, they are very different. At a 500 meter scale resolution, less than 15% of the two datasets agree. That means that they are super different. Another example that makes us face a bit of difficulties is that we looked at topography. So we used the JEPCO project with this very nice 500 meters resolution. So here we see a part of the Great Barrier Reef, and we're happy to compute the slope at these locations. And we wanted to have a look at the distribution of coral reefs at global scale regarding depths. It's quite nice what we get. So I do not come back on the distribution itself, but the fact that at least for the two datasets, Allen Coral Atlas in blue and the orange one for the UNEP WCMC dataset, the distributions are pretty the same. Okay, but we were quite surprised to see that when we look at the distribution with the slope, I mean they really like when there is no slope. And what Johnny Klippas did a long time ago now, in the late 90s, she showed that, I mean, she used the topography factor in her model, saying that the higher the angle is, the topography angle is, the better it is for coral reefs. So it seems that this does not hold with the values we have, the data we have. Well, when we sum up all of this, and we try to move forward, I mean, we build a certain habitat module for our coral reefs. So here you have the distribution of coral reefs depending on different environmental parameters, temperature profile, etc., etc. And you see our distribution, the distribution we get with our strategy with the black solid lines. And you see that we are pretty close to something which is good. But I do not show you maps here. And if I show you maps, you would be like, yeah, it's not so good. Yeah, it's not so good. It's very difficult. Why is it difficult? I think it can be it can be summed up by one sentence from Schmidt and co-authors 2018, is that a coral reef can become trapped in a seaweed-dominated state in the same conditions under which corals thrive. So it makes it super difficult, basically, to get a proper habitat distribution in which we can be fully confident. Well, we have already started the second step regarding heatwave sensitivity. This will be done using our coral reef habitat module and a synaptic intercomparison, trying also to play with heatwave sensitivity tests, especially adaptation as well. And then, so this will build up kind of an biogeographical information that we'll be happy to share at some point. And then the next steps are regarding calcium carbonate production and dissolution, which will enable us to get kind of a physical chemical information and really go back to what we're interested in, coral reef carbon feedback. And for this, and we Tyler started to say a few words about that, but we would like to be able to consider maybe two different coral reef functional type, at least for calcification. We're focusing on calcification dissolution. Maybe massive versus branching corals, but what about calcifying algae as well? Because they seem not to be as sensitive to heat waves each other. So it might be really interesting and also important to take into account different um, tendencies in calcifying organisms regarding future projections. And so, yeah, exactly, this will build up kind of a physical chemical information at the end. It's time for me to finish there. Just it's difficult to talk about coral reefs without saying a word about how important they are also in terms of biodiversity aspect, as Taylor said at the beginning. It's difficult to finish without a call to action and even a call to outcome. It's so important when we speak about coral reefs, when we speak about Benthic calcifiers, not only to speak about this carbon feedback or impact on the carbon cycle, it's also super important to discuss biodiversity aspects, to discuss socio-economic aspects. So, yeah, and especially for policymakers, I think. And I'll finish there.